Okay, ladies and gentlemen, this is our second video. Let me choose my pointer. Yeah, this is our second video on metric spaces, and in this video I'll be talking about neighborhoods of a point in the metric space, open and closed balls, and open and closed sets. And I'll talk about the distance between a point and a set, and the distance between a set and a set in a metric space. So let's begin with the general idea of the distance between two sets in a metric space, or a point and a set in a metric space. Okay, so this is our metric space XD, the blue area, okay? And we have, so this is X, this is the metric D, and we have a point here, okay? And this is another point, and this is a point, this is set A, and this is a set B. Okay, now basically speaking, this point is totally outside the set. It's not even on the boundary of the set, okay? Whilst this point is on the boundary of the set, and this one is totally within the set. Well, we want a precise way of saying that, you know, the point is far from the set or is close to the set. We want an idea of distance between a point and a set. And that is what we are going to define in this video. And we can also talk about the distance between a set and another set. For example, the set A and the set B. Okay? If you look at this diagram, you might say, well, the distance between A and B is positive. Why? Because they don't seem to intersect. But we will see very soon that, well, that is not the way it is. You can have two sets in a metric space where their intersection is empty, but the distance between the two objects is not empty. So let's go straight forward to a more precise definition of the distance between a point and a set in a metric space. Okay, so you have a metric space XD, okay? And then you have a subset of X, which is a subset within the metric space. And you have a point in the space, or in the set X. Now this point may not be in the set S, okay? The distance between this point and the set is given by this thing here. This is the notation. So this is the metric, this is the point, this is the set. And it is the infimum of all these distances. Now notice that this is simply the distance between A and every other point in the set. So we look at these values and we take the infimum of these values. Now the important thing to note in this definition is that it's the word infin or infimum or inf or whatever you want to call it. This is quite different from minimum, because we all know that if you have a set, the minimum of the set will always be the infimum of the set. But if the set has an infimum, it may not be the minimum of that set. So infimum is not always minimum, but minimum, if there's a minimum, is always infimum. And there's a very good reason why we use infimum instead of minimum. Okay? So let's look at a typical example. So we have a metric space. The set is R, and the metric on this set is the Euclidean metric. Now, if you have a point 0 and an interval 0 to 1, the distance from 0 to the set is 0. But if you look down here, you realize that it's the same thing, but we have an answer 1. Why is that so? It is because the distance from a point to a set actually depends on the metric you define on the space. In this case, if the Euclidean metric, we give a distance of 0. But if we use the discrete metric, we get a distance of 1. Why is that so? In the first video, we said that the discrete metric on R, or any set, is the metric that does the following. The distance between 2 points is 1 whenever the points are different. And the distance between 2 points is 0 whenever the points are the same. Now, because 0 is not in this interval, the distance from 0 to any point in this interval has to be 1. So if you look at all the collections from 0 to all the points in this interval, you're always going to get 1, 1, 1, 1. And so that means that in this set, you're always going to have 1s. And so the infimum is 1, which in this special case will also be the minimum. So please take note that if you talk about the distance from a point to a set, you must always ask whoever is asking you that question, what is the metric on the space? So you cannot talk about distance between a point and a set without referring to a particular type of metric. Take that and remember. Okay, so now we can extend this idea to distance between two sets within a metric space. So you have a metric space xd and you have a subset S and another subset T. The distance between these two objects is given by the following definition and notation. Now, this is a more general case than the distance between a point and a set. Okay, but once again, it's basically the same thing. It is the infimum of all these distances, where A comes from the set S and B comes from the set T. So you evaluate all these distances and you take the infimum. If there is a number, if the infimum exists, then that would be the distance between the two sets. So let's look at an example here. But before we do that, you have to remember the distance between two subsets of a metric space can be 0 even if their intersection is empty. And to see that, we give a very simple example here. Suppose we have the metric space or the set R, and the metric on this set is the Euclidean metric. Then of course the distance between this interval and this interval is 0, even though the intervals have no element in common. And that is because, well, we are dealing with infimum. And you can evaluate this and check for yourself. If the word here was if the word here was minimum, then of course this thing would not be well defined. Okay, because then of course the distance here wouldn't be 0. Okay, so this is very important that you pay attention to this thing right here. Okay, now this brings us to the idea of the diameter of a set. Well, in elementary school, almost all of us learned something about circles. And we know what we talk about the radius of a circle and the diameter of a circle. Well, a circle in most cases is a collection of points. So you have a set of points. So you can talk about the diameter of a circle. Well, the diameter of the circle is simply the largest possible distance between the points within the circle. Right? That forms the circle. So we can generalize this idea to the diameter of any set within a metric space, since we are talking about distances between points. So you have a metric space xd and you have a subset of this metric space. What is the diameter of this set? Well, we say the diameter of this set is 0 if the set is empty. Okay? And the diameter of the set is a supremum of these distances whenever the set is not empty, and you can find the supremum. But if you cannot find the supremum and the set is not the empty set, then the diameter of the set is infinity. Oh, please, this is infinity, okay? So please take note. Whenever a set is empty, the diameter of the set is 0. If the set is not empty and you can find this supremum, then the diameter will be the supremum of this set, where you have all the possible distances between two objects within the set. If the set is not empty and this supremum cannot be found, then we say the diameter is what? Infinity. In special kind of infinity here. This is positive infinity. Okay. So let's look at a practical example. Now we have our metric space X, and we have a subset A, which is the black rectangle, and we have another subset B, which is the green ellipse filled in. Okay. Well, if you look at this, you might say, well, the diameter of A should be equal to the diameter of B, because you are looking at the distance from this point to this point. But that's not true. Remember, diameter means you have to look at all possible points, collection of points, or pair of points within the set, and then you take the supremum. Well, if you look at A, we can take a point right here, and we can take another point here. And the distance from this point to this point is clearly going to be greater than the distance of any point here to any point here. So that means that, well, the diameter of A is expected to be greater than the diameter of B. And that is exactly what is the case. The diameter of A should be greater than the diameter of B. So there are some facts about diameter and of a set. For example, if you have a metric space and you have two subsets, then one thing is very clear, that the diameter of S has to be 0 if and only if S contains at most one point. Remember, at most one point means that you can have one point within the set or no point at all. And of course, if S contains no point, then it's empty. And from our previous slide, we saw that, well, that means that the diameter of an empty set should be 0. Now, if S contains just one point, then there is only one point within S. And so if we go to our previous slides, it means that you're always going to have XX here. and therefore the supremum will be 0. The other thing also is that if you have a set which is a subset of another set, then the diameter of this set S should be less than or equal to the diameter of T. And that's exactly what we saw in the previous slide. Here, because B is a subset of A, and so we expect the diameter of B to be less than or equal to the diameter of A. And similarly, if the two objects, the two sets are non-empty, their intersection is non-empty, then we expect the diameter of their union to be less than or equal to the sum of their diameters. So the diameter of S plus the diameter of T. So this brings us down to the idea of open and closed balls. So suppose we have a metric space XD, where D is the metric on the space, and we have a point which is in the set X, and we have a number delta which is positive. Then the open ball with radius delta and center A is given by this. This is the notation. Remember, anytime we talk about open ball within a metric space, some things are very important. One, we need a radius of the ball, we need the center of the ball, and then we need to know what type of metric is on the set. So this notation is very important. And so what is this? This is a set of all elements within the metric space such that the distance from those elements to A is always less than delta. Similarly, we can define the closed ball with radius delta and center A. All we have to do is to replace less than with less than or equal to. So in other words, if you look at the open ball, the points on the boundary of the ball or the circle are not included within the set. However, in the case of the closed ball, the points on the boundary are all included. And to see this, we can have a very simple example. For example, depending on a given metric and a given set, well, the open ball could look round like this. In fact, this open ball comes from a very special type of metric on R2, because this is in the plane. So you see the dotted lines on this set implies that the points on the boundary are not included within the set. So any point within the set, the distance from that point to A will be less than what? Delta. So this is an open ball for a given metric in R2. And we'll see very soon what this metric is. On the other hand, the closed ball, the points on the boundary are included because we said less than or equal to. So there's a clear difference between an open ball and a closed ball. And by convention, usually open balls, we will use the dotted lines to denote that the ball is open. And for closed balls, we will use a full line to show that the points on the boundary are also included. So let's see an example of where this ball came from. So let's take a point A, which is A1 and A2. This point happens to be in the plane, which is R2. Okay, so the open ball with radius delta centered at this point in this metric space where D happens to be the Euclidean metric is a set of all points in R2 such that the distance from xy to this point is less than delta. But we saw before that the Euclidean metric, the distance from this point to this point, is given by this object right here. And so when we plot all these points out, we will get something like this. So in other words, the Euclidean metric on R2 will always lead to an open ball of this form. But then you might ask yourself, does it mean that every time you have a metric in R2, the open ball is going to be like this? The answer is no. Let's see why that is so. Suppose now we use the same point, but we change the metric from the Euclidean metric to a different metric, which is defined in this form. Then in that case, the open ball centered at A with radius delta will look like this. And this is not the same as the previous ball that we saw. So it's obvious to you then that open balls really depend actually on the metric on the set. You cannot talk about open balls in a given metric space without referring to the metric. Okay, so now we come to the idea of the neighborhood of a point. So let XD be a metric space, and let's take a point which is in the set X. We have a subset of X. This subset is said to be a neighborhood of A. If you can find a positive integer or a positive real number, if you can find a positive real number such that the open ball with this radius centered at A, given this metric, is a subset of N. In other words, N is a neighborhood of A if we can have an open ball centered at A with some radius, and that open ball is totally contained within N, then we say N is a neighborhood of A. Remember, let me just make this very clear. When we talk about a neighborhood of a point, the neighborhood can be open or closed, but that's not very important for now. All we want to say is that if a set is a neighborhood of a point, then it means that there is an open ball centered around that point that is totally contained within our set. So we have a very simple example here. So this is our metric space XD. This is a subset of our metric space, which of course is N. And we can see that, well, this N happens to be a neighborhood of the point A. Why is that the case? Because we can construct an open ball with radius delta. This open ball is centered at A and is totally within the set N. It's a subset of the set N. And so N is a neighborhood. Remember, the definition says there exists an open ball. It does not mean that every open ball centered at A should be a subset of N. All we want, all that is sufficient, is that you can find at least one open ball centered at A with some radius, and that open ball is contained within the set N. So now we can say some things about the neighborhood of a point. Now, the first statement is that if you are in R, for instance, the interval AB is a neighborhood of all its points. Well, somebody might say this is wrong, and the person is right. If you want to talk about neighborhood, you must always talk about the metric in question. This statement is true if the metric is the Euclidean metric. So if we have the Euclidean metric on R, then this interval AB is a neighborhood of all of its points. However, with the same metric on R, this interval is a neighborhood of every point except A and B. Why is that so? Because if you look at the point A, any open ball centered around A will definitely not be contained within this interval. Some part of the open ball will be outside. The open ball is going to contain some elements of R which are on the left side of A, and so that open ball cannot be a subset of this interval. Furthermore, we have the set of integers is not a neighborhood of any of its points if the metric is the Euclidean metric. Now you see I said if the metric is the Euclidean metric, because this statement will be false if the metric is a discrete metric. So remember, when you talk about neighborhood of a point in a metric space, you must always pay attention to the kind of metric you are dealing with. Because when you change the metric, certain statements might not be true anymore. The third thing to understand is that if you have open balls centered around a given point, or you have a neighborhood, different neighborhoods around centered on the same point, then the intersection of all those neighborhoods is also a neighborhood of the point. As provided that that collection of neighborhoods is finite. Which means that you can have an arbitrary collection of neighborhoods centered on a point A and their intersection may not be a neighborhood of A. Well, there is no example in this video, but you can check that out for yourself. Okay, then we come to the last component here, which is the idea of a closed or open set in a metric space. So now we have a metric space XD, and we have a subset of this set X. We say that A is open if it is a neighborhood of all of its points. That is, for every point in A, we can find a radius. Well, this radius positive depends on the point X, right? Such that this ball centered at X with this radius is a subset of A. If you can do that for every point in A, then we say A is an open subset of the metric space. A typical example. Now, if you look, for example, at this set here, you see this is a dotted line, which means that this is an open set. All these objects are open sets because we use dotted lines to denote them. And they are all open. But this one here is not open because we don't use dotted lines, which means that the points on the boundary of this set are included. This set is not open. In fact, this set is closed. Why? Because it contains all of its boundary points. You see, this point here, X, we can find an open ball centered on X which is a subset of this set. But if you look at the point y, every open ball we put around y, no matter how small that ball is, there is always going to be part of that ball which is outside of the set. And there's always going to be part of it which is inside the set. So a point like y is said to be a boundary point. For example, this guy is a boundary point and this guy is a boundary point. Now, when all boundary points are included within a set, we say the set is closed. So a closed set in a metric space is an open set union all the boundary points of that set. So for example, if you look at this set, this is an open set within the metric space. But if we include all the boundary points and we add that to the set, what we have is a closed set. Now, a point like this is said to be an interior point of the set. Why? Because we can always put a ball around it that is a subset of the set. However, this point y is not an interior point. That's what I call this point a boundary point. Because no matter how small your open ball is, it would never be a subset of the set.